Hello, and welcome to our review podcast on our Earth structure unit. This unit has 4 objectives, and like we've done before, we're going to go through them one by one. So objective number 1 is to calculate and compare the densities. So if we're looking at the various layers of the Earth, like atmosphere, hydrosphere, crust, mantle, outer core, and inner core, you should be able to tell me which is more or less dense, as well as calculate density. So here's some review. Here's our density formula. My favorite memory trick is the heart trick, but by all means use whichever works for you. So if we layer or order the different layers of the Earth from the lowest density to the highest density, hopefully you can see that the farther out you get, the less dense it is. So the inner core is the most dense, while the atmosphere is the least dense. Let's look at a density calculation problem, just in case it's been too long. So remember, our formula is mass divided by volume. So if I have a rock and it has a mass of 2 grams and a volume of 10 milliliters, what's its density? So I set it up so that I have the 2 grams over the 10 milliliters, which would make its density 0.2 grams per milliliter. How about another one? If a rock has a density of 5 grams per milliliter and a volume of 10 milliliters, what's its mass? Now this one is a little more tricky. In order to do it, I need to set it up so that 5 is equal to the unknown mass divided by 10 milliliters, so our mass should be 50 grams. Here's a model of the models of the Earth by density, and that is actually why they layer. Now, there's 2 different ways to name the layers, and we've gone through a few of them, but the big thing to remember is that the more dense is in the middle, like the inner core, and the least dense is towards the outside, like the atmosphere. And because the different layers have different densities, that actually causes the layers to form. Objective number 2, compare the density of the objects to the density of known Earth materials. So here's a density table. Notice it gives you the atmosphere, the ocean, the crust, the mantle, and the core. Let's look at a problem and see if we can determine which layer it would fit most closest to. So if I have a mass of 1,930 grams and a volume of 100 cubic centimeters, I set it up 1,930 divided by 100, which gives me a density of 19.3 grams per centimeters cubed. So that's my first half. The second half, let's go back to the table. I need to find which layer either includes or is closest to the density of 19.3. And based on my chart, that would be the core. It has the largest, so it would be closest to the core. Next thing we could do is to use this information to make a model. So we want to use relative density, which substance would be which layer of the Earth. If we look at this chart, cotton has the smallest density, so we would make that equivalent to the atmosphere. Glue has a density of 1 grams per milliliter, which is the same as density of water, so that would be our hydrosphere. Things like the nickel being the most dense would need to be our inner core. So you'd want to be able to use some logic to reason through which layer would be most represented or be most clearly represented by which substance. So here's one last little bit reminder of density. Don't forget the formula, mass divided by volume, determines where objects will settle. Will they settle towards the bottom if they're more dense? They will settle towards the top if they're less dense. Things like the core is made up of iron and nickel, so those are usually a good thing to use to represent it. And think back to your density tower, what you were able to put in and what worked and what didn't work. So objective number 3 asks you to model the different layers of the Earth based on density. So let's go through and take a minute and talk about the different layers of the Earth. The inner core is in the center. It is made of nickel and iron, and it is a solid. So the particles in there are moving very, very slowly. It is extremely hot in the center of the Earth, but because of the amount of pressure that's pushing on those particles, it does actually force it to remain a solid. The outer core is also made of nickel and iron, but it is liquid, so it is moving a little faster in relation to the speed of the particles. The mantle is made up of a lot of elements, including things like oxygen and silicon and magnesium. Not a huge thing to know the different components, but just so that you can know. It is our largest layer of the Earth, and it is not really a solid or a liquid. We give it the term plasticity, which means kind of like Play-Doh. You can slowly move it, but if it starts to move too fast, it can actually crack. So think of it like somewhere slightly more liquid than a solid, but not a pure liquid. The crust, or the lithosphere, is also made up of a lot of different elements like oxygen and silicon. It is a solid layer. It is the layer on which we live in, where you're standing right now. The hydrosphere is made up of water. These are things like oceans and lakes and rivers and streams and groundwater. Its density is 1 gram per milliliter, since it's made of water. The atmosphere is our last layer. It's made of various gases. It is the least dense layer of the Earth. It is on the outside. So what does density have to do with the different layers of the Earth? Here's the rule again. The further in you go, the more dense it is, and the further out you go, the less dense it is. So the reason why we see the layers layer the way they are is because of the different densities of each of the layers. Okay, mini quiz time. See if you can answer these questions. Which layer is the thickest? A, core, B, crust, C, mantle, D, hydrosphere, E, atmosphere. Correct. C, mantle. Or you may have got it wrong, but the answer is mantle. Which layer is the densest? Same choices. A, core. Which layer do we live on? B, crust. Hopefully none of those threw you for a loop. They were pretty basic. Let's move on to objective number 4. Objective number 4 asks you to look at models of the Earth and to be able to tell whether something is correct or incorrect, or to scale or not to scale. So first let's get to how we know what the layers of the Earth look like. Our most significant piece of technology is called the seismograph. Basically the waves from earthquakes. There are a few different kinds: P waves, S waves, surface waves, shear waves. We didn't talk about these in very much detail, but you should know that depending on the substance and the state of matter that it is, the waves will act in different manners. So they will change direction or change speed, so to indicate whether it's a solid or a liquid. We have a variety of models and a variety of ways to measure these, as simplistic as a hanging ball that can vibrate as the waves pass through, to more complicated things. Let's look at some pictures. This picture on the left is a raised relief model. If you've ever felt one of those globes that are really bumpy, that's the kind of model we're talking about. They're great, they have a lot of good things about them, but one of their major flaws is the mountains are extremely tall. So if we were to draw the mountains to scale, based on the size of the Earth, you wouldn't be able to see them or feel them. But if you look off to the side, especially in this picture, you can physically see the mountains. So that would be one inaccuracy of the raised relief model. Let's take a minute and talk plate tectonics. It's not specifically on your test, but it is something that you do need to know. So things I want to remind you of: that the lithosphere, or the crust, is not a solid surface, that it's broken into plates. We've got oceanic and continental plates, and they ride on top of the asthenosphere. That's that layer that again, has that characteristic plasticity, which means it is moving slowly, but it's not totally rock solid like we would think a solid. Things are moving at approximately 10 centimeters a year. Depends on the plate and depends on the location. But we have some things, or some observable evidence, that demonstrates to us the plates are moving. So we have fossils on different continents. Think about how the continents kind of look like a puzzle. We can look at the oceanic floor and see the movement and the new creation of new crust at that point. We can also measure earthquakes and volcanoes and mountains. Those are all natural phenomena that occur at plate boundaries. And then, just to be kind of cool, we have satellites that can actually pinpoint and literally measure as they move. So those are your 4 basic objectives, the things you need to know for our test. Thank you for listening. I hope it helped, and good luck.